So let's have a look at this conical pendulum in a little bit more detail. So there's good old Bob, and Bob was travelling around in that horizontal circle, and I was attempting to give it constant angular velocity, so it made a nice, neat circle as it was going round. Just put some dimensions in there so we can work with the problem. The string made an angle of theta with the vertical. Obviously there's a height to the cone and there's a radius to the cone as well. We start by drawing our force diagrams. So what forces are acting on this particle? I don't bother putting in the resultant force here because I'm going to break it up into a horizontal component and a vertical component. I just want to know all the forces that are actually acting on this particle. And so there would be tension up the string, right? Because there's a string attached to the particle. As I said yesterday, anytime you've got a string attached to the particle, you have tension, and its direction is up the string or away from the object. And we also have the force due to gravity going down. But that's it. They're the only forces coming into play. Now, the interesting thing there is the tension, because it's not vertical and it's not horizontal. So we'll have a component of horizontal tension and we'll have a component of vertical tension, because again we want to simplify the problem and turn it into straight line motion. So we'll look at vertical forces and horizontal forces. So as I said, theta will be the angle and omega is our angular velocity that we're travelling at. So the resultant forces, what do we have? Well, the resultant force horizontally is our mv squared on r, or our mr omega squared, depending on whether you're using linear velocity or angular velocity. Vertically, it's nil. Right? Because until I increased its velocity or decreased its velocity, it stayed in the same horizontal circle. So whilst it had constant velocity, it didn't move up or it didn't move down. So therefore, there are no forces acting on it vertically as a resultant. So the way I do this, I go, let's have a look at the horizontal forces. I know all the horizontal forces will result to be the centripetal force, the mv squared on r. And all the vertical forces will sum to give 0. So let's say tension, I'm going to have to break up into a horizontal and a vertical. So I'll have one going to the left and one going up. There's Bob. So horizontally, all we have is that one horizontal component of tension. That bit of trig, we can say, well, that's T sine theta, because it's the opposite side to theta, so we must end up with sine theta. So therefore, T sine theta is mv squared on r, or mr omega squared if we're using angular velocity. Vertically, I have the component of tension going up, and that would be cos theta, because it's the adjacent side to the angle, and then mg is totally vertical. They would add together to give 0, but of course they're in opposite directions. Doesn't really matter which one you make positive there, because they sum to give 0 anyway. And so I could say T cos theta is mg. So I now have these two equations that I can play with to find different results out. One of the common things we do is say, well, let's combine it and get rid of the tension. So I go T sine theta over T cos theta, the tensions will cancel. And I just get sine theta on cos theta is mv squared on r times 1 on mg, and I get a way I can find the actual angle. If I know its velocity and I know the radius, I can sub in and get the angle. Or I could rearrange it if I wanted to find the radius or if I wanted to find the velocity. With angular velocity, that would turn out to be r omega squared on g. But then I could have a look at the original dimension triangle that I drew, and tan theta in that was the radius over the height of the cone. So if I sub that in, I can now come up with another formula. V squared on rg would equal rh, and again I could rearrange that depending on what I want to find, but the height of the pendulum is equal to r squared g on v squared. But what's more interesting is if I do it in terms of angular velocity, it just becomes g on omega squared. So the height of the pendulum is totally dependent on the angular velocity, because g obviously would be constant. And it's inversely proportional to its squared. And that's why when I sped it up, it rose. Because the faster the angular velocity went, the smaller the height of the cone. And slow it down, it would drop down. So there's some of the implications that then comes out. So the depth of the pendulum below A is totally independent of the length of the string. Other than, of course, it couldn't go further down than the actual length of the string because it's attached to it. And as I say, as the speed increases, good old Bob rises. Oh, well, let's have a look at this problem then. So we've got a conical pendulum, and I'm going to increase the number of revolutions from 60 per minute to 90 per minute. We want to know, well, how much will it rise? So I'm increasing the angular velocity, it will rise. So all the problems I start the same, and that is draw my force diagram. So I've got tension up the string, gravity going down. It's going to be the same force diagram pretty much for every conical pendulum. I'll need my components of tension, but also I'll need those dimensions of the cone, so radius and height. Then I say, all right, I know the horizontally all that's happening is circular motion. So I know all the horizontal forces will sum to be mv squared on r. And I know vertically nothing's happening until I actually change the velocity. So vertical forces will all sum together to give 0. So left, I've got t sine theta, because horizontal is opposite the angle there. So t sine theta, and in this case, I'm going to do it in terms of angular velocity, because we've been given one of 60 revolutions per minute, so that's going to be easier to work with. And vertically, component of tension up the string, and then mg, they will sum to give 0. It's basically exactly what I just did. And then I'd come up with our formula, just as I did before, by putting t sine theta on t cos theta. I get tan theta is r omega squared on g, but we know, looking at our dimension triangle, tan theta would be r on h when we look at the cone. So there's my formula, h equals g on omega squared. Now I can use that to find the height. So initially, 60 revolutions per minute works out quite nice to be 2 pi radians per second. And so the height at that point is g on 4 pi squared. 90 revolutions per minute, well, you know, works out kind of neat as well. 3 pi radians per second. That was lucky. Sub that in, I get g on 9 pi squared. So the amount that it's risen must be the difference between those two. So it's risen, and an approximation for that, using 9.8 for g, comes out to be 0.14 metres. It's risen. Here's an interesting one that appeared in the 2002 paper, where we got a conical pendulum, but it's also resting on a cone. So it's a conical pendulum on a cone. That's kind of cool. Or is that just me? All right. So our particle of mass m, we've got the string length L. It's sitting above this cone. A particle remains in contact with a cone and rotates as a conical pendulum, angular velocity omega. They've given us some angles here. The angle of the cone at the vertex is 2 alpha, and alpha, we're told, is greater than pi on 4. String makes an angle of alpha also, with the horizontal, they've given us the angle there. Force is acting on the particle. Of course, they remind us that, yes, there'll be tension up the string. The other thing is this normal force. Whenever you make contact with a surface, there's what's called a normal force, or a reaction force, sometimes you see it called. It's the reason why I can stand here and not collapse, because gravity is acting on me at the moment. So why don't I just collapse due to the force of gravity? Well, there's a force that balances it out going upwards, which is the reaction force, and they balance out, hence I'm able to stand here. So whenever we are in contact with a surface, we have this reaction or this normal force, and of course we have the force due to gravity as well. Show with the aid of a diagram that the vertical component of that normal force is n sine alpha. And of course, when you look at this question, if you got it in the test, you'd start groaning because it says, with the aid of a diagram. We know how we love drawing our diagrams. Right, here's our force diagram. There's good old Bob. Tension going up the string. But there will be a component there. Now I've got to work out where alpha is. Alpha will turn out being there because if you look at the original picture, alternate angles, I can say alpha would be down there. Normal force. And with that one, I can draw a triangle. Now, where's the alpha? Let me just draw it again over here. Remember, it's sitting on this cone. And the angle at the cone was 2 alpha. So by symmetry, I know it's just alpha with the vertical. Now I can play around with this because vertically I'm going to get alternate angles. So that's alpha. That therefore means up the top is alpha because remember, the normal force is perpendicular to the surface. So the little angle in there must be 90 minus alpha. Thus, angle sum of a triangle gives me alpha is up in the top right-hand corner for that force diagram. And we've got gravity going down. Now, I don't need all that information to answer the question, but I'm going to use this information later on, so may as well, because we just want the n sine theta. Let's call that vertical component C so I can answer this question. So basically, I'm trying to find C, and it's just a bit of trig in this triangle now. So I can say, oh, look, C over n is sine alpha, so C is n sine alpha. It now wants me to show that the tension force plus the normal force is mg on sine alpha, and then find an expression for tension minus the normal force, but in terms of the mass, the length of the string, and the angular velocity. Right. Horizontal forces will sum to give mr omega squared. It's still a conical pendulum, it said. So it's circular motion horizontally. So let's draw that diagram up. Horizontally, component of tension. This time it's going to be cos alpha, because alpha's down here, and horizontal is now adjacent to the angle. So it'll be T cos alpha. And horizontally, again, it's adjacent to the alpha. So I'll have n cos alpha going to the right-hand side. So T cos alpha minus n cos alpha is equal to mr omega squared. Remember, the positive direction has to be towards the center of the circle. Because as we confirmed very convincingly yesterday, the centripetal force is always going towards the center of the circle. All right, let's have a look at vertically. Vertically, it's still going to be 0. So we have the component of tension will be T sine alpha. We've got a component of the normal, and we've got gravity acting down. They will all sum together to give 0. Playing around with that, I get T sine alpha plus n sine alpha is mg. Now, what are we trying to find? We're trying to show that T plus n. Well, I think if you have a look at my vertical forces one, it's quite a simple thing. All I've got to do is divide both sides by sine alpha now. And to find an expression for T minus n, if I look at my horizontal one, all I've got to do is divide by cos alpha. But that's not what they asked me to do. They said they wanted it in terms of mass. Okay, I've got that there. But they said length of the string. I need to get L in there. All right, if we go back to the original question, we can see using the dimensions that radius over the length of the string is cos alpha. So I could substitute that in for cos alpha. The radius would end up cancelling, and I get ml omega squared. The angular velocity is going to increase until n equals 0. So the instant you lose contact with the surface, there's no normal force anymore. It's only when you're in contact with the surface that you'll have a normal force. So that instant it lifts off the surface, normal force becomes 0. It's no longer in contact. So we're going to increase the angular velocity, and we saw that means that the bob will rise. At the point where it rises and loses contact with the surface, that normal force is going to equal 0. So that's the point we're interested in at the moment. So it's just about to lose, that instant. We're now going to find an expression for this value in terms of the angle, the length of the string, and gravity. Well, if n equals 0, I can simplify the two expressions that we just worked out. So now I know the tension will just be mg on sine alpha, but it'll also be ml omega squared. Well, it's the same tension, so now I can eliminate tension out of this. So mg on sine alpha will be ml omega squared. Let's see, they said in terms of alpha, length of the string and gravity. Yeah, I just got to make omega the subject. And playing around with it, there it is, we get the square root of g on L sine alpha. Ta-da! So it's the Cambridge 9b as opposed to the Patel 9b, because the Patel 9b is not about conical pendulum. Patel 9c is about conical pendulum.